Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Network topologies describe the structure and layout of how devices are connected and how they communicate with each other. These topologies are not just theoretical diagrams, they directly influence how data moves, how systems respond to failure, and how efficiently resources are used. Whether it's a simple office network or a complex data center backbone, understanding topology helps define both physical layout and logical behavior. From initial design to day-to-day maintenance, topologies guide how devices interact and how networks evolve over time. For the Network Plus exam, topology knowledge is foundational. It appears across multiple domains, particularly in sections on network architecture, design planning, and troubleshooting. Questions often require you to distinguish between physical and logical designs, or to identify the characteristics of specific topology types. Topology awareness also influences your ability to assess fault tolerance, understand broadcast and collision domains, and determine where and how devices are likely to be placed within the infrastructure. One of the earliest and simplest topologies is the bus topology. In this layout, all devices share a single transmission medium, typically a coaxial cable. The signal travels down the line and is available to every device along the path. Terminators are placed at each end of the cable to prevent signal reflection, which would otherwise cause interference. While efficient in small deployments, bus topologies are highly sensitive to faults. If the central cable breaks, the entire network can go down. Another early topology is the ring topology, where devices are connected in a circular configuration. Each device has exactly two neighbors and passes data in a single direction around the loop. The signal travels from one device to the next until it reaches its destination. Variations of the ring topology include token ring networks and dual ring implementations that allow for redundancy. Though rarely used today, ring topologies were once valued for their predictable traffic flow and collision-free design. The star topology has become the dominant design in modern networks, especially in local area networks. In this layout, all devices connect to a central hub or switch. This central device acts as the communication point, managing data flow between endpoints. If one cable fails, only the device connected to it is affected. Other parts of the network remain operational. This makes the star topology easy to manage, troubleshoot, and expand. The centralized nature of this design also simplifies performance monitoring and traffic control. Mesh topologies introduce the concept of path redundancy. In a mesh network, devices are connected to multiple other devices, creating multiple paths between any 2 points. This increases fault tolerance, as data can reroute if a connection fails. Mesh is common in backbone networks, high availability environments, and wireless mesh deployments, where resilience is a priority. Mesh networks are robust but come with increased complexity and cabling requirements, making them less suitable for small-scale use without clear justification. Within mesh networks, it's important to distinguish between partial mesh and full mesh designs. A full mesh connects every device to every other device, maximizing redundancy but requiring a large number of links. In contrast, partial mesh limits connections to only the most critical nodes, balancing resilience with cost and complexity. Partial mesh is more common in practical deployments, especially in high availability, and others do not. Hybrid topologies combine elements of multiple basic topologies to meet specific needs. A common hybrid example is a star bus topology, where groups of star-connected devices are joined using a shared bus. Another example is a ring-star hybrid, where rings are interconnected through a central point. Hybrid designs are especially prevalent in large, layered networks where no single topology type is sufficient. These models reflect the real-world complexity of networking infrastructure, blending reliability, scalability, and cost efficiency. It's also important to differentiate between physical and logical topologies. The physical topology describes how devices and cables are arranged. The logical topology refers to how data flows between devices, regardless of their physical placement. In switched Ethernet environments, for example, the physical layout might resemble a star, while the logical topology operates more like a bus. Understanding both views is critical for troubleshooting and for interpreting how protocols like spanning tree and VLANs operate over physical connections. Device placement is heavily influenced by the chosen topology. In a star topology, central switches or hubs are the focal point of connectivity. In a bus topology, all devices attach along a single backbone cable, often making troubleshooting harder. In mesh designs, backbone routers and distribution nodes are positioned to ensure multiple communication paths are available. Placement decisions based on topology impact redundancy, fault domains, and signal integrity, making them critical during network planning and deployment. Different topologies also affect how faults are detected, isolated, and resolved. For instance, a star topology simplifies fault detection because each device has a dedicated connection. Failure on one link doesn't impact others. In a bus or ring topology, a single failure may disrupt the entire network. Mesh designs limit the scope of failure by offering alternative paths, but their complexity can make isolating the problem more difficult. Understanding how topologies influence fault domains helps shape a troubleshooting strategy and limits the scope of diagnostic work. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Network topology has a direct influence on performance characteristics across both small and large environments. The layout determines how bandwidth is distributed, where congestion is likely to form, and how collisions are handled. In a bus topology, all devices share the same medium, which means that only one device can transmit at a time, leading to collisions in legacy systems. In a star topology, each device has its own dedicated connection to a switch, reducing collision domains and improving bandwidth allocation. Mesh networks further enhance performance by offering multiple routes, which helps distribute traffic and balance load dynamically. Topology choice also shapes how fault tolerance is implemented. Mesh networks, particularly full mesh configurations, offer excellent fault tolerance because each device can reroute traffic if a link fails. This design minimizes downtime and supports critical applications. Star topologies offer moderate fault tolerance. If a cable to one device fails, only that device is affected. But if the central hub or switch fails, the entire network may be compromised. Bus and ring topologies are more vulnerable to single points of failure. Any disruption in the main line or loop can impact all connected devices. The complexity of installation and ongoing maintenance varies significantly between topologies. Full mesh requires many connections, which increases cabling costs and demands careful physical planning. However, once installed, it can be very resilient. Star topologies are relatively simple to install and maintain. Adding or removing a device typically involves a single cable, making them ideal for office environments or classrooms. Ring topologies require more effort to ensure signal continuity, and troubleshooting them can be more difficult due to their sequential structure and reliance on continuous loops. Scalability is another crucial consideration. Star topologies scale effectively with the availability of ports on the central switch. As long as ports are available, new devices can be added easily. Mesh topologies, however, do not scale linearly. Every new device added to a full mesh requires additional connections to every existing device, resulting in exponential growth in link count. Bus and ring topologies are limited in scalability due to signal degradation, collision potential, and the physical limitations of cable length and termination. Each topology type also carries cost implications. Mesh topologies, especially full mesh, are expensive due to the large number of links and the hardware needed to support them. However, this cost can be justified in mission-critical environments where redundancy is essential. Star topologies strike a balance between cost and functionality, requiring centralized devices like switches, but keeping cabling costs manageable. Bus topologies are inexpensive in terms of materials, but are rarely used due to their performance and reliability limitations. Passive components, such as terminators and simple coaxial cable, were once cost-effective, but are largely obsolete today. Use cases for each topology type help contextualize where they are most effective. Star topologies dominate in LAN settings such as homes, schools, and offices due to their simplicity and ease of expansion. Mesh topologies are commonly used in backbone networks, data centers, and wireless mesh deployments where interrupted communication is critical. Hybrid topologies are increasingly common in multi-tiered environments such as enterprises with multiple floors or departments. These hybrids may use star layouts at the access layer, with mesh connections at the core to ensure redundancy and resilience. Understanding the evolution of topologies helps explain why certain designs have become dominant. Bus and ring topologies were more common in early network implementations, but have fallen out of favor due to their inherent limitations. The widespread adoption of Ethernet and the affordability of switches contributed to the rise of star topologies, which offer better performance, scalability, and fault isolation. Mesh and hybrid designs reflect modern demands for uptime, path diversity, and complex service delivery across multi-layered infrastructures. On the Network Plus exam, you may encounter questions that require you to identify or map a topology based on a diagram, description, or function. Visual recognition of layout types, such as identifying a ring from a circular cable path or distinguishing a mesh from a web of interconnections, is a common exam theme. You might also need to compare the benefits or drawbacks of different topologies based on performance, cost, or fault tolerance. Understanding the real-world implications of each design helps guide accurate, exam-aligned answers. In summary, network topologies define the physical and logical framework of how devices connect and communicate. They determine how signals travel, how failures are isolated, and how services scale as the environment grows. From simple bus lines to full mesh architectures, each topology introduces its own trade-offs. By mastering the distinctions between them, you gain insight into how networks are constructed and how they perform under different conditions, insight that is critical for both exam readiness and real-world network design. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.